Hello, everyone. All right, just a few announcements before we get started. So next week is the last week of classes, so there'll be a final summary lecture on Tuesday, and then the optional COVID-19 lecture on Thursday. We're also coming to the end of assignments for the class, so there's one last lab today. There's the last homework, which is due on Tuesday. If my advice would be to try to get all the labs and homeworks done by next Thursday if you can, because that's when the final project is going to be going out, and that'll be due on May 7th. So please try to stick to that May 7th due date, unless you can email me if you need an extension beyond that. But that is intended to be the date for the final submission of everything for the class. For that final project, you have that whole week to work on it. You don't have to pick a specific window. It's a little bit longer than the other projects. It's not hugely longer, but you can just have the flexibility to work on that anytime. All right. Any last logistics questions before we start for today? Okay. So today we're going to be talking a little bit more about Bayesian statistics. And so on Tuesday, we started out talking about Bayes' rule, right, and how we can use this to try to get these conditional probabilities of our belief that some hypothesis is correct based on data that we've collected. But there's actually a lot of other kinds of topics in Bayesian statistics, and one of the popular ones has to do with model selection. So the intuition for a lot of this work comes from Occam's razor, which you probably heard before, which is just that we would prefer to have simpler explanations when we can. So if there's two possible explanations for some data or some phenomenon, if they both fit the data equally well, we'd prefer the one that's simpler. And so this idea is also referred to as parsimony, that right, we want to have our scientific theories, we want them to be as simple as they can be. Right, it's okay to add some extra complexity to our theories if that helps explain the world, but we shouldn't add unnecessary complexity. And so we've talked about this issue a little bit in the sense that, for example, if we're just evaluating how well our model fits on some particular set of data without using some extra testing set, then more complex models will almost always explain the data better, in the sense that they have more moving parts that we can use to line up with things that are happening in the data. But a lot of what they're capturing might just be sample specific things. So they're not really capturing something about the world. And so this makes applying this kind of tricky. And right, of course, in reality, we never have two models that explain the data exactly equally well, right? There's always going to be some difference between models and how well they explain the data. For example, right, we talked about different kinds of effect sizes or things like variance explained, right? How much of the variability in the data can we predict with some kind of model? And since more complex models almost always account for more of the variance, the question is how we can apply this this kind of Occam's razor. And so we've talked about one method for doing this, which is making predictions on a held out test set, right? So we use one set of data to set all the parameters in our model, and then we lock our model and are forced to make predictions on some extra data. But there's another approach, which is trying to figure out how to balance this variance explained and model complexity in the same data set, right? And the intuition here is that if we make our model a lot more complicated and it only captures a little bit more of the variability in our sample, then that's probably not worth it, right? That we've added a lot of complexity to our model. It doesn't seem like it's only captured a little bit more of the information about this sample, and it's probably captured nothing more about the actual population that we care about, right? What's actually happening in the world. So when we're doing this model selection, we want to have a way of kind of penalizing models that are too complicated, right, for the amount of variance that they're explaining. So we're going to work through an example here. So let's imagine we're trying to figure out a model that can predict people's risk of depression. And so this model is looking at two potential genetic variants that might be related to depression. And so we don't really know what the connection is, right? So there's, we could think about, we have sort of four hypotheses, which is that gene 1 is related to depression. So a particular variant of gene 1 increases risk for depression. Only gene 2 is related to depression. Both of them influence your risk of depression, or neither one is related to depression. And so again, in Bayesian statistics, we don't have to think about just sort of a single null model that we're trying to reject. Here we just have four sort of equally good, potentially, hypotheses, right? And we're trying to figure out which of these we should believe the most. I mean, we might have some prior beliefs based on other data. Maybe we want to be kind of skeptical in general. So our prior here is to think that neither of them is related to depression. That would be the kind of skeptical prior, that we think, in general, most genes are not related to depression. But right, the idea here is we want to figure out the evidence for each of these. And so in this lecture, I'm going to be using the term hypothesis and model kind of interchangeably, right? Because at least this kind of hypothesis that we're talking about here is basically a model, which is if we want to predict someone's risk of depression, how should we do that? And one type of model uses just gene 1, a different type of model uses just gene 2, a different type of model uses both, and a different type of model uses no genetic information at all. Like, that model would basically just predict some constant value for every person. So we've discussed some kinds of classical frequentist tools for answering questions like this, which would be basically just doing a chi-square test, right? So for example, for gene 1, we could take our sample size of 250 people, and we can break these people down into these four categories, right? Most of the people in this group are not diagnosed with depression and don't have this gene variant. And then there's some other people in these other three categories, right? And so what we can do is do a two-way chi-squared test to test whether there's some relationship between the columns and the rows here. Is there some relationship between having this particular genetic variant and your risk of depression? And so if we run that chi-square test, here we get like a super, super tiny p-value, right? And you can sort of see why that, like, so if you don't have this genetic variant, you're overwhelmingly likely not to have depression. If you do have this genetic variant, then you're more likely to have depression than not, right? So this shows a pretty strong interaction between these two things. We can do a similar thing for gene 2, right? So here we've split up our data set into these four bins, these 2x2 bins. And we can run a chi-square test. And here, again, we see an effect size that's not as strong, but we do still get a p-value that would cause us to reject the null, right? And so here, this classical way of, this classical frequentist thing is, right, we're testing whether the null hypothesis, which is that there's no relationship between G2 and depression, is that a good explanation of this data, right? And our answer here would be no, that this data looks unlikely under the null hypothesis. We can also do a third kind of chi-squared test, where we test whether both of these genes, as well as their interaction, has some impact on depression. And again, if we run this, we see a very strong effect. We didn't actually talk about doing a three-way chi-squared test, but it's basically it just has slightly different degrees of freedom, right? But it's the same idea. We're just asking whether there's some relationship between the columns and the rows here, right? And this is telling us there is. We could also look at things like effect sizes and risk assessments here. For example, if we want to build up what these models actually would be in terms of making predictions, we can just figure out what the likelihood is of being diagnosed with depression given your particular genetic makeup. And so, right, we'd start out with priors. So in this data set, 14% of the people are diagnosed. So that would be our prior. And so if we're a model that doesn't use any genetic information, would predict a 14% chance of depression for every person. If we want to build a model that just uses gene 1, we have to know what is the probability of being depressed having this gene and not having it, right? So our model that only uses gene 1 we would measure this gene in a person, and if they have this gene, we would say there's a 70% chance they're depressed. If they don't have the gene, we'll say there's a 9% chance they're depressed, right? This is our model, our prediction model that only uses G1. We were going to adjust our predictions based on whether people have this gene or not. We could do a similar thing for G2, right? Maybe this is a model that only uses G2. We measure this in a person, and then we can adjust our prediction. So instead of just predicting 14% for each person, we're going to predict either 17% or 8%, depending on your genes. And we could also have a model that uses both. Right, and so this kind of model, we measure G1 and G2, and we have 4 possible predictions depending on the outcomes in this particular person. And so this, right, if you measured both G1 and G2, then we are going to have a 75% chance. If this person has neither of these variants, then there's going to be a 3% chance, and we have predictions for the in-between cases as well. Okay, so we have these 4 possible models. And our chi-squared tests basically tell us that all of them are good, in the sense that all of them, that we would reject the null in every case, right, doing our chi-squared tests. Right, and so the question is, what does this actually mean? Like, what if we actually wanted to use this as a model in real life? Which one should we use, right? We rejected the null for all of them. Does that mean that, like, all of them are true? And we also haven't taken the complexities of these models into account, right? So the G1 and G2 model, adding both genes is always going to improve our fit for any sample, but we don't know whether it's actually going to help in the population, right? It could be that maybe one of these genes or the interaction between these genes is really not useful, and we can explain extra stuff in our sample because we've sort of fine-tuned these parameters of our model, right? We've fine-tuned these probabilities to work well in this particular sample. But is this extra complexity worth it? Are we actually going to improve our predictions in the population? And another problem with the traditional frequentist approach is that we can't get a measure of evidence in favor of the null model. Right, the null model here is just we predict 14% for every person, and we can't really get a measure of like how good that model is relative to the other 3. Right, the null model has kind of a special status in our classical statistics that's the only one we're trying to reject. It doesn't really like compete on some even playing field with the other 3 hypotheses. So one approach here is referred to as Bayesian model selection, which is that we're going to try to measure the evidence for each of these models, meaning we're going to measure how well they fit the data. And this measure of fit has a built-in correction for model complexity, meaning that as our model gets more complicated, it's going to have to explain more of the data for it to be a good model. And this measure of evidence we're going to talk about today is called the marginal likelihood of the model. So we've actually seen this marginal likelihood before on Tuesday. It's another name for the normalizing constant that's in Bayes' rule. So if we wanted to use Bayes' rule in this case, right, if our goal here is based on measuring something about people's genetics, we want to make a prediction of whether or not they're depressed, right, or what their risk of depression is. And so we talked on Tuesday about, right, just writing out the rules for conditional probability. We can write this down like this, which is that we're going to take your prior probability of risk for depression, and then we're going to multiply by this kind of conditional evidence. What's the chance that if you were depressed, what's the chance you would have this genetic makeup? And then there was this kind of mysterious term in the bottom that on Tuesday, we figured this out just by kind of summing across the possible hypotheses and setting this normalizing constant so that our conditional probabilities here are summed up to 1. And so this thing in the bottom is called the marginal likelihood. And so what this thing is right, this is saying this is the probability of the data, which is the genetic measurements that we're making in this person. And so probability of the data might sound kind of weird, but right, what this means is how likely is this data that we got under the current model that we're using. And so another way to think about this is that this is a probability distribution over all possible data sets, right? So In this case, there's only 4 possible data sets, right? You can either be positive or negative for each of these genes. But you can imagine in a more general setting, there's like a continuous, like infinitely big number of possible data sets you could have gotten, right? But this is a probability distribution over all of those data sets. And it basically says what kinds of data this model thinks are likely versus unlikely. And so this is a good way this is at least one way to measure how much a model actually understands the world. If a really good model should know what kinds of data sets are likely versus unlikely. A good model should understand, for example, the correlations between the different things that you're measuring. So it should understand what a good realistic data sample would look like versus an unrealistic one. And so this normalizing constant here is right. It's kind of measuring how good this model that we're using is at understanding what the data distribution actually looks like. So at least in simple cases, like the example on Tuesday and this example, this is easy. This term is easy to compute, right? All you do is you do the prior times the evidence for each of your hypotheses, and you sum them up, and then whatever that 1 over that sum is this normalizing constant. And we could get a different one of these for each of our models. So this probability of genes, we'd get one of these for each of our 4 possible models, right? The sort of null model, the G1 model, the G2 model, and the combination model. So one problem is that in sort of real life, this is a real life example as well, but for a lot of the kinds of things we measure in psychology and neuroscience, our data sets are really complicated. So we're measuring continuous valued things. We're measuring lots of things at a time. And so actually computing these can be really hard. So there are a bunch of modern techniques for how to compute these things. Some of them involve just like brute force computing. There's actually some ways to get around computing this explicitly. You can kind of compute approximations to it. And we're going to talk today about some kind of sort of simple approximations we can use to estimate this thing, right? But the intuition here is that for any particular model, we can measure this P of the data on our data set. And that's going to tell us something about how good of a model this is for this particular data. So just to give another example of this, on Tuesday, I talked about a model we use in my lab for tracking brain activity while people are watching movies and describing movies. And so the way that model worked is that we for every scene of the movie, for every like event of the movie, we had some pattern of activity of what your brain looked like during that movie. And then we would divide up after we divided up the movie into these events, we'd look for these events to be reactivated in your brain while you're doing recall. The problem is that there's a parameter in that model, which is how finely should we slice up the movie into these events, right? So I think in the example last time, I was imagining there's like 35 different scenes in the movie, and we're trying to look for how people are talking about those 35 scenes. But 35 might not be the right number, right? We might not know what the right time scale is for how events are represented in the brain. And in fact, different brain regions maybe have different time scales for how they represent information. So one thing we can do here is consider many different models with different numbers of events. And we can just look at this marginal likelihood term, right? This denominator term, to see which of these models is explaining the data the best. The graph I'm going to show, I'm actually plotting the log of this, right? But it's the same idea that higher values mean the models are better. So what we did here, each line here is applying these data to these models to slightly different data sets, which is not important for right now. But so we have a bunch of these different models with different event lengths. So some of these models have really tiny events, some of them really long events. And so we look at this marginal likelihood for all these models, and we find that for this particular brain region, the best models have events that are something like 30 to 60 seconds, something like that, right? And so what this lets us do is try to evaluate for different brain regions what time scale of information are they representing, right? And so this brain region here, it seems like it represents kind of a minute or so of the narrative, right? Because that's the model that has the best marginal likelihood. So there's a question in chat about how this differs from a p-value. And so this is different from a p-value in a few ways. So first of all, this is when we're doing this, we're going to get a marginal likelihood for every possible hypothesis. So the p-value is basically it's something like how well the null model explains our data, right? So you get the p-value is sort of like the marginal likelihood for the null model. They're not exactly the same thing, right? But it's the same concept that you could test how well the null model fits our data, and that's kind of what a p-value is telling us as well, right? But here now we're going to get this marginal likelihood evidence for every one of our hypotheses. So we're going to get it for the null. We're going to get it for if we just have a single alternative hypothesis, we're going to get one for that as well. Or like in this example, we have 4 hypotheses, and so we're going to get 4 values out of this, right? We're going to get 4 measures of how well these 4 different models work. Okay, so before we start doing math, let's just do a quick quiz here. So this marginal likelihood that we're trying to compute, what does it depend on? A, the model we're using, B, our data, C, the prior probabilities of our hypotheses, or D, both the model and the data. Okay, so if we want to compute a marginal likelihood, what do we need to specify? Okay, yeah, I'm seeing some D's, which is right, which is that right. What the marginal likelihood is measuring is how well some particular model fits on some particular data set. So we need to specify both the model and the data. For most of these examples, the data is going to be constant, right? Like we're going to collect a particular data set and we're going to evaluate different models on that same data. But you could also look at different data sets, right? In the example I was showing here, each of these lines here is like a different data set that we're testing our models on. And it's nice. So you can see the model fits a little bit better on some data sets than others. That's why some lines are higher than others. But all of them show this nice bump around the same number of events, or the same event length, which is sort of a good indication that these are the best models, right? These models are the best across different data sets. Okay. So there's I guess one more concept we're going to talk about before we do math, which is the idea of a Bayes factor. And so the Bayes factor allows us, these marginal likelihoods allow us to compute something called the Bayes factor, which is one of the sort of main outcomes often in a Bayesian analysis. And so it plays a similar role to P in the sense that we're trying to compare hypotheses. And we could compare, for example, compare the evidence for our alternative versus the evidence for the null. And so the Bayes factor, all that this is the ratio of marginal likelihoods between 2 models, right? And so it's the measure of the relative weight of the evidence for model 1 versus model 2. And it's marginalized over the outcomes. What we mean is that we're not actually interested. This measure doesn't it doesn't depend on how well the model predicts like individual outcomes, like depression and being not depressed, right? This is just an overall measure on the data set that's independent of the particular outcome measures, right? There's no conditioning here on depressed or not depressed. And so these marginal likelihood measures tell us something about the fit between our model and our data. And so if a Bayes factor is bigger than 1, that means that model 1 is a better fit to our data, right? That means that the numerator here is bigger than the denominator. So a Bayes factor that's larger than 1 means that the marginal likelihood is better for model 1. For Bayes factors less than 1, then that means the model 2 is doing better than model 1. So for example, if in a paper you see that a Bayes factor of 5, what that means is that the marginal likelihood for model 1 is 5 times as good as the marginal likelihood for model 2, right? Which means that model 1 fits the data 5 times better than model 2 does. And so unlike a p-value, right? So a p-value is essentially just measuring something like what the evidence for the null is on this data set, right? How well the null fits this data. And so first of all, we're usually not going to do like a binary reject, fail to reject thing like we do in null hypothesis testing, right? We're just going to have this continuous value where a value of 1 means the models are equally good, and the Bayes factor can get bigger and bigger to say that model 1 is getting better and better relative to model 2. And the nice thing here too is we can actually compare two hypotheses, right? So instead of just asking what the evidence for the null is, we're going to compare, for example, we could compare the null model to some alternative model, some specific alternative model, right? And ask which of these fits the data better and by how much. The other nice thing is we could compare two hypotheses where neither of them is the null model, right? So maybe, right, in this depression example, right, we have 4 different models, and we might want to know, is the gene 1 model better than the gene 2 model, for example? Neither of those is a null model, so it's kind of unclear how you would try to ask that question with null hypothesis testing, right? But here we can just compare the evidence for any two possible hypotheses. And so here's sort of a rough interpretation chart for these Bayes factors. Obviously, this is just hand waving, but Bayes factors that are sort of above like 10 or so would be considered strong evidence in favor of model 1. Bayes factors that are less than 3, but between 1 and 3 means that model 1 is kind of trivially better than model 2, right? And so again, we try to stay away from like specific thresholds in Bayesian statistics, right? The part of the idea here is that we can accumulate evidence over many experiments for these things. And so, even a Bayes factor of 3 is maybe meaningful if we can combine it with other evidence or something, right? But yeah, so this is sort of telling us how much better one model is than another. Okay, and so another nice thing about these Bayes factors is that they automatically correct for model complexity. So if you have two models that are equally complicated, so they, for example, we have two models that each depend on one gene, then this is just measuring how well those models fit the data. But if you have a model that's much more complex, then this Bayes factor sort of automatically accounts for that in the sense that getting a good, if a marginal likelihood of this complex model is better than the marginal likelihood for the simple model, that means that it must fit the evidence a lot better because there's going to be these kind of implicit penalties in the Bayes factor for complicated models. So this is at least one kind of mathematical version of an Occam's razor, right? Which is that this fit automatically corrects for complexity. Right, p-values do not have this property. They're just telling you if the data are surprising given the null. And so they don't really directly adjust for complexity because you don't really specify what the other model is. And if you do something like a many-way chi-squared where there's like many possible predictors, that's a very, the null there is kind of very complex, which is that the null assumes that none of these predictors have any relationship to the sample. And so as you add more and more and more predictors, it's sort of that kind of complicated model, right? It could be easy to, it's kind of easy to reject the null in the sense that almost certainly one of them is going to relate to something in the sample, even if it doesn't in the population. Okay. So let's do, before we work out how to actually compute this Bayes factor, let's just do one more quiz here. So if I say that there's a Bayes factor of 10 for model 1 versus model 2, what does that mean? That model 1 is 10 times more complex, model 1 fits the data 10 times better, model 1 would require a data set 10 times larger, or model 1 is 10 times faster to compute. Okay, so how would we interpret the Bayes factor of 10? All right, great. Yep, the right answer is B, that this is a measure of model fit. And it does have a built-in kind of correction for model complexity, right? But it's really, this is supposed to be a model fit measure. And so it doesn't, the space factor doesn't tell you anything explicitly about the complexity of the models. And it doesn't tell you anything about like how much data you need or how fast it is to compute, right? It's just this measure of how well these two models fit this data. So yes, there's a question about the downside of Bayesian testing. So actually I'm going to spend like the last 20 minutes or so today talking about some of the debates about when to use these Bayesian models. Definitely one of the problems which I mentioned is actually computing this Bayes factor can be really hard to do. And especially in the neuroimaging models I mentioned, for example, in my lab, like the only way we can compute this is by doing like by making tons of assumptions, basically, many of which are probably not that accurate. And so this is one problem, is that these things are a little hard to compute. There has been a lot of work in the statistics world over the past 10, 20 years or so, especially now that we have faster computers, about ways to compute these things. The other problem, honestly, another problem is simply that people are a lot less familiar with this Bayesian stuff. So, I sneak a little bit into this intro class, but this is not something that psychologists are normally trained in. And so when reporting results, you want to do it in a way that the field can understand. And so null hypothesis testing has really been the default for so long that there's sort of some momentum or some inertia to overcome to actually to switch things. But at least for these kinds of simple models, the Bayesian versions of these things are pretty easy to compute. Okay. So the question is, how do we actually compute these Bayes factors? And so one approach, there's this way to estimate the Bayes factors, which is called the Bayesian Information Criterion, or BIC. And that has this formula. You're not going to have to use this formula, but I'm just going to show it to you to show what it looks like. Let's see. Okay, hopefully my streaming is doing okay there. All right, so you don't have to know this formula. I'm just going to show you what it looks like, which is that the log of the marginal likelihood, the negative log of the marginal likelihood can be approximated with this complicated formula. So this first thing, C, is just some unknown constant that cancels out between models, so we don't care about that. This second term here, K, is the number of free parameters in the model. This is something sort of like the degrees of freedom of models, right? So how many sort of moving parts do they have? And the N here is the size of the data set. So this term here has to do with how complex the model is. And then this last part is the likelihood function for each observation, right? So these are the evidence terms in Bayes' rule, right? Which is that assuming this model is true, what is the likelihood of each of our data points? And so the negative here is this is like the convention we use for BICs, is that it's the negative log, which means that the logic is flipped. So low BICs means that the model is better. I'm not sure why this convention is used. It makes it confusing. High, you want big marginal likelihoods, which means you want a small BIC. This term basically comes from this field of statistics called information theory, and in information theory, having a model that's hard to describe has a lot of information in it. And so we want our model to be easy to describe, meaning that it's a simple model that explains the data well. The sign here is flipped, which is annoying. So BICs, we want BICs to be small for models, right? Small BIC means that the model has a large marginal likelihood. And so you can see in the terms here, right, there's this first term is basically a kind of complexity penalty. So if K is really large here, then that means that you're going to have a big positive term here, which is bad for us, right? That's going to increase our BIC. So complex model is going to have a big penalty here. And then this term here is about how well the model explains each of our data points, right? And so for a good model, this last term, this minus last term here is going to be a big negative number, right? Because it's going to fit the model really well. So the probabilities are going to be large and we're subtracting them, right? So we're kind of balancing here. This is complexity and this is model fit. And we're subtracting the two of those to figure out how good is this model relative to its complexity. Okay, so let's try to actually get back to our example here with the genetic study. So let's try to calculate stuff using this this formula. So first we need to know what K is here. And so in this case, for the no effect model, K is 0. There's no parameters in that model. K is 2 for the single gene models and 4 for the 2 gene models. You could basically think about how many degrees of freedom there are in those chi-squared matrices. So there's 2 degrees of freedom for our 2 by 2 chi-squared, and there's 4 degrees of freedom in that big 3-way one. So when we compute these BICs, again, you won't have to actually work this kind of BIC measurement yourself, but when we compute these BICs, we get a value here for every one of our 4 models. And so what we want is a low BIC here, right? And the lowest one is this first one, where we just look at gene 1. Right, so 85.7 is the lowest value here. And so so we can basically look at between these things, right, and see, for example, this G2, the model here that only uses G2 is actually worse than the null model by a little bit, right? Even though we got a significant result, meaning that under a normal null hypothesis test, we would have rejected the null here by a hair, right? It was P of 0.04. But when we actually use these marginal likelihoods, right, what this is telling us is that this extra complexity of measuring this genetic component in this person is not really worth it. It fits the data a little bit better, but the extra penalty we get for having these 2 extra degrees of freedom means that it actually gets an overall worse BIC than the no effect one does. Right, and so this is kind of an interesting conclusion that we couldn't get from a p-value, right? We can never assert that the null is true. We can't even really totally assert that it's false, right? But we could reject the null at least. But we didn't, in the normal null hypothesis framework, there's no way to say that the null is a good model. But here we can, right? We can see for each of these 4 models, we have some measure of the quality of them, right? And we can rank them. And again, the null hypothesis is just another one of these models we can compare. And so remember, the BIC is the negative log of the marginal likelihood. And so the Bayes factor is a ratio of marginal likelihoods, which means that it's going to be an exponential difference between the BICs, right? So BICs are like in log space here, right? So we have to subtract them and take an exponent of them to get back to a Bayes factor. And so and also notice the order here, right? So since BICs are in the opposite direction from Bayes factors, the Bayes factor for model 1 versus model 2, we need to actually take BIC model 2 minus BIC model 1, which is also annoying. Yeah, there was a question about the last slide about, right, what's the difference between rejecting the null and saying the null is a bad model? They're pretty similar. The main difference is that when we do null hypothesis testing, the only model we actually consider is the null, right? So we have the null model, we see how well it explains our data, and the p-value tells us how well the null fits in our data. We don't actually like explicitly specify an alternative hypothesis in null hypothesis testing. Right, and so we can't. It makes it kind of hard to compare whether, like, even if the null is not a good model, it doesn't mean that our alternative is a better model, right? So that's kind of what happened here, is that the null is not a great model. The BIC here is bigger than some other models we're testing, like the G1, right? This difference between 85 and 94 is a pretty big difference in BIC. So the null model is not very good, and it makes sense to reject it. The problem is that this alternative is also not that good. So measuring G2, it like fits the data a little bit better than the null, but not more than we'd expect just based on, so even if there is no real great relationship between G1 and G2 and depression, we would expect a little bit of a better fit just from having these extra 2 degrees of freedom. And so once we apply that penalty, then this one is not as good. Yeah, the results we get with these Bayesian analyses also can be a little different than the normal frequentist ones, right? Because we're setting up our hypotheses a bit differently, and so yeah, so especially for sort of borderline cases of like p of 0.04 is also we can get different answers here, right? But the main point is that we're asking here a different question, right? Which is that we can evaluate sort of the goodness of all of these models, including the null, right? And compare them. And we can also compare between models that are not the null here, right? And see which of them is better. Okay, so so we can compute Bayes factors just by subtracting BACs and then taking the exponent. So for example, if we want to compare the G1 model versus the G1 and G2 model, right, we just take their BACs, subtract them, and take the exponent of them, right? So we take e to e squared here, basically, right, is 7.54. We could also compare these two models, right? So this Bayes factor model, the Bayes factor of G2 versus the null model. Here is saying the null model is a bit better. And so, right, this would tell us that the evidence supports that the G1 model 7.5 times as much as well as the 2-gene model, right? Meaning that adding that extra gene is not helpful, right? It adds extra complexity to the model and doesn't increase our fit by that much. So yeah, there's also a question about what if all our models are bad, which is obviously a bad situation to be in. But the nice thing about this Bayesian framework is that at least we can know that's the situation we're in, right? We can evaluate that maybe not only is our null bad, but our alternative explanation is also bad and also doesn't fit the data, right? And so that tells us that we need to search for better models, right? Or I mean, it could be that our data is just completely junk and there's no model that fits it, or it can mean we need to find a new model, right? And that's a good thing to know from our data set. Right, that's something that again, like null hypothesis testing can't really tell us that much, that just because the null is a bad model doesn't mean that our favorite hypothesis is the right model. Okay, so as we were saying, this BAC formula we're using here is kind of a pain. It involves like computing these conditional likelihood things on every data point and stuff, which is not very easy to do. But it turns out that in a linear regression framework, there's actually a simplified version of this BAC formula that's pretty easy to use. And so it looks like this. So the BAC for a model is, again, there's some constant offset, which doesn't matter. That's going to subtract out. Anytime we subtract two BACs, this is going to disappear. So this doesn't matter. And then the other terms here is K, again, is the degrees of freedom of our model, and is the number of data points. And then this last term here is our mean squared error for our model. And so, first, I guess let's talk about K first. So K is the, in at least a simple linear regression, K is the number of predictors plus 1, which means that the number of predictors here is basically the number of coefficients in our linear regression, plus the slope also counts as a predictor. And then we add 1 on top of that. So in like a simple slope and intercept model, so a simple linear regression where we just have a single variable with a slope attached to it, and then we have an intercept, and then we add 1, this would give us K equals 3. For an ANOVA, K here is the number of groups plus 1. And so this means that we can that we can compare any sort of model that counts as regression. And remember, ANOVAs are basically regression in disguise also, right? Then we can put into this framework. So all we need to know is this K, which is sort of a measure of like how complicated our model is. And then we also need to know this MS error, which we'll talk more about in a second. But right, in our ANOVA, this is a term we compute. In other kinds of regression, the analogous version of this MS error is something like the residuals of our model, right? So this is saying how many mistakes we're making here. And so you can see our BIC, we want low BICs, right? And so if we make our model more complicated, that's going to increase our BIC. And if we have bigger errors, that's also going to increase our BIC. Unfortunately, exactly calculating marginal likelihoods is much more complicated. These BICs are just sort of approximations. The value here depends on prior beliefs, meaning prior beliefs about the distribution of the data. And the math is often kind of impossible to compute. But at least under certain kind of assumptions, we can use this BIC measure. Again, this is making a particular assumption about the penalty we should apply for complexity, which doesn't hold in all situations. But at least in a simple regression framework, this can work. Okay, so if we want to compute BIC for a regression model, what do we have to measure? Right, we're gonna fit some regression model, and what do we need to measure from that model? Okay, so here are your choices. I'm just gonna I'm gonna yell at my dog. I'll be right back. So think about this for 1 second. All right, sorry about that. I'm back. The dog is, well, yeah, we got him from a shelter, but he's like some kind of Chihuahua Yorkie thing, something that loves to bark. Okay. So, all right, so yeah, I see D's, which is great, right? That's the only thing we need to measure from our regression model is this MS error. Okay, so the nice thing about this kind of regression BIC is that we can actually use this to compare lots of different kinds of models, like any model that fits in a regression framework, which is actually pretty much everything we've talked about this semester. So as long as each model is trying to predict the same Y, then even models with very different kinds of predictors can be compared to one another. So yeah, so that's another example here. Let's say we're trying to characterize depression rates in 50 states using different kinds of models. And so the sort of simplest model is just using the mean and variance, right? So let's just try to have some mean prediction across every state. Maybe we have another model that, for example, knows like which religion is the plurality in each state and tries to make a prediction based on that. Maybe we have another model that predicts depression using a social connectedness index, which is some continuous measure of how socially connected people are in that state. And so obviously this is just an example. Probably none of these would be great depression models, right? But the idea here is that these are all very different kinds of models that have different kinds of predictors. And so right here's our sort of simplest model, which is just predict the mean depression rate with some variability around it. We could do an ANOVA, which predicts within each of these different religious groups, predicts a depression rate. Or we could have a continuous valued model, right, that takes in this continuous social connected measure and then output some prediction of depression rates. Right, so in each of these models, we could get a kind of residual variance. In the t-distribution, this is simply the sample variance, right, the sample standard deviation squared. In the ANOVA, this is MS error or MS within, depending on the kind of ANOVA we're doing. And in linear regression, this is the variance of the residuals, those epsilon residuals. And so, right, so we can measure these for each of our models, right? For each of these models, we get some measure of how much variability in the data is still left after we apply our model. Right, and so the idea is that since these are all trying to predict the same variable, which is this depression rate, we can actually compare these residual uncertainties to each other. Okay, so we can calculate these BICs for each. So we're going to use this formula from a couple slides ago, this regression BIC formula, which is, right, so the MS error is going to be the second term, and then we need to figure out this first term. We need to figure out what this K is for how complicated each model is. And so for the the one sample t-distribution, which we're just predicting the mean, that has just one group. So its k is 2, the number of groups plus 1. So we can work out its BIC. We need to plug in k, and we need to plug in n, and we need to plug in the variance in this model. So we get a BIC of negative 18. Whether the BICs are positive or negative doesn't matter, right? All that matters is the difference in BICs between different models. Our ANOVA has 3 groups, so k is 4. We can plug that in to get a BIC. Finally, our regression has 2 predictors. It has a slope and an intercept. So we add 1 to get 3, and we have a BIC for this model. Right, and so in this case, again, we want BICs to be low. And so the winner here is this continuous regression model, right? At least among these 3 models, the continuous regression one is the best. And so again, we could also compute a Bayes factor between these models by just taking the difference in BICs and then taking the exponent of that. So in practice, right, one of the questions here is, even after you have the best model, what should we do with the other models? And so, right, so for example, right, this, right, for predicting depression is maybe kind of complicated. Maybe even though the religion model was not as good as the social connectedness one, maybe we don't want to ditch it entirely, right? Maybe it still has some extra value. And so a nice thing we can do with these Bayesian methods is that we don't have to actually reject any of the hypotheses, right? Remember, we're just trying to like adjust our degree of belief in these different models. And so we can actually, what we can do is assign a weight to each model that's based on its BIC or based on its Bayes factor. So what we can do, right, is we just keep all of our hypotheses around. We have a different weight on each of them depending on how good we think they are. And then we can combine all of these models together in a weighted model average. And in this model average, our best models get a bigger say than the less effective models. But every model sort of gets a vote, right? And so this kind of model averaging is also called an ensemble prediction, right? Which is that we have lots of models, they all get to make a prediction, and then we combine them where the way we combine them is weighted by which models we think are better than the others. And so these kinds of ensemble predictions are really popular. One reason is because if we have models that depend on different kinds of data, then they can help kind of correct each other's errors, right? And so any individual model is going to have like weird failure modes. And so if you have an ensemble of models together, the hope is that they can kind of patch up each other's mistakes, right? And so even if one model is technically the best, the other models might still be good because if you give them all some kind of small vote, then if that main model makes a mistake, maybe the other models can correct it. So this is not really, these ensemble predictions are way less common in psychology, but they're super popular in lots of kinds of data science domains. So for example, financial models are almost all this kind of model because you don't want your financial model to only depend on, you don't want your financial prediction to only depend on one model that only has a certain type of information, right? You really want to hedge your predictions. You only want to make a big investment, for example, if all of your models are in agreement about what you should do. Anytime you're trying to predict a complex system like weather, you almost always use these kinds of ensemble predictions. Or if you're trying to predict things where there's lots of uncertainty for things like models of climate change, we usually use multiple underlying models. And again, they're not all on equal footing. Some of these models we know fit the data better than others. But by combining them, then we can make much more robust predictions. Okay, so to sum up it's basically to sum up the Bayesian stats part of the class here, right? Today we talked about Bayes factors, right? And think about what Bayes factors means, what a Bayes factor of 6 would mean, for example. And right, we can use these Bayes factors to compare models. We can compare a model to the null, but we can also just compare different models, different interesting models to each other. We can approximate these Bayes factors using BIC. And we can compute ensemble predictions by weighting models by the goodness of their fit to the data. Okay. Any last questions on these topics? Okay. So I want to spend the last 20 minutes of class just zooming out a little bit to talk about just in practice, what kind of methods should we be using, right? We spent a lot of time in the class talking about these traditional frequentist methods, and now I'm telling you about some advantages of these Bayesian things. And so there's lots of disagreement both within the statistics field as well as within psychology and neuroscience about what kinds of methods we should be using. There's lots of fights about these things. Here's some actual comics from a pro Bayesian statistics blog. Right, here's the Bayesian people that are sort of masters of data analysis. And meanwhile, here's the frequentists, right, that are just clinging to their p is less than 0.05 and just blindly rejecting null hypotheses, right? And so, this kind of stuff is kind of silly, but there is there are some legitimate questions here about which of these approaches makes the most sense. And so, just to give you some sort of balanced perspectives here. So one view is that the nice thing about p-values is that they don't really require many assumptions, especially if you use something like a permutation test. You're making some assumptions about the sampling method that you used, but besides that, you don't have to make any assumptions about, for example, your prior belief in certain hypothesis, in a certain hypothesis, right? And so this is really nice for science because it means that the p-value you report is pretty much a direct function of the data, and you don't have to get sidetracked with fights about how likely you think things are before you see the data, right? That this is maybe the right way that scientists should be talking to each other, is just with these p-values. Another sort of pro-frequentist position is that these Bayesian methods are kind of cool, but they're very complicated. They often have lots of assumptions in them, and people aren't well trained to use them. And so maybe we should just stick to these frequentist p-values. They're easier to use. We don't have to try to figure out our priors and all this kind of stuff, right? And so this I think also is just a practical reason why people often use p-values, is because they're much easier to compute. You don't have to plug in lots of assumptions into your, you don't have to plug in lots of assumptions about, for example, your priors, or about, especially if you want to do things like compute these Bayes factors. They require complicated methods with lots of assumptions. On the other side, right, the pro-Bayes argument is that, first of all, they're governed by the rules of probability theory, right? Bayes' rule itself is just like a direct consequence of the definition of conditional probability. And so this is kind of nice because if our end goal is to compute something like the probability that a hypothesis is true, we should do that using actual probability rules and not just using our own intuitions about p-values or something. And so, yeah, there's a question about whether prior knowledge is confirmation bias, which can certainly be true. If you, it's confirmation bias in the sense that if you start with a super strong prior belief, then any typical experiment is not really going to change your mind. It's not confirmation bias in the sense that if you have a strong prior belief in something, evidence will eventually change your mind, right? With enough strong evidence. The worst kind of confirmation bias is where when you see some evidence against your position, you actually reject it and don't shift your position at all, right? Or maybe become even more polarized towards your original position, right? So Bayesian methods won't do that, but they will. It could be that your starting point is very much in favor of some hypothesis, and it's going to take a long time to drag you away from it. It's going to take you a lot of evidence. There's another argument in favor of Bayesian statistics, which is that interpreting the results of Bayesian analyses maybe is actually easier than interpreting p-values. And so this is, again, the thing people fight about a lot, but is, right, if you run a Bayesian analysis, you might get something out, which is something like based on this data, conditional on this data, the probability of your hypothesis being true is X%. And that's a relatively easy thing for people to understand. Whereas if you say, right, a p-value for this data is 0.02, maybe people don't understand what that means. Maybe, right, especially if reporting to the lay public, people don't understand what that means. And maybe even people that are in the field doing statistics don't totally understand what a p-value means most of the time. And so this is a reason not to use frequentist p-values, right? Is because people misinterpret them. So one of the studies that Bayesians like, one of the kinds of studies that Bayesians like to cite here is studies where they ask people in the field, both students as well as researchers, to interpret p-values and then see if they can actually answer correctly what it is. So I'm going to run one of these studies on you now. This is intended to be a little bit challenging, but the studies look like this. So they'll give you a scenario. So suppose you have a treatment you suspect may alter performance on a certain task. You compare the means of your control and experimental groups, say 20 subjects in each. And you use an independent means t-test, and your result is that you have a p-value of 0.01. So I'm going to show you 6 statements, and for each statement, I want you to think about whether that statement is true or false. When we get to the end, we're going to I'll ask you to type in which ones you think are true. Okay, so I'm going to show 6 statements here about what this p-value of 0.01 means, right? So again, the setup is we're doing some intervention. We have a control experimental group, and we have a p of 0.01. We obtain a p of 0.01 in this experiment. Okay, so for each of these 6 things, think about if you think any of them are true. It could be that all or none of them are true as well. Okay, so statement 1 is you have absolutely disproved the null hypothesis that there's no difference between the population means. Right, so the null hypothesis here is that there's no difference, and this is saying that because you have a p of 0.01, you've absolutely disproved the null hypothesis. Okay. All right, number 2, you have found the probability of the null hypothesis being true. 3 is you have absolutely proved your experimental hypothesis that there is a difference between the population means. 4 is that you can deduce the probability of the experimental hypothesis being true. 5 is if you decide to reject the null hypothesis, the probability that you're making the wrong decision. And 6 is that you have a reliable experimental finding in the sense that if you repeated the experiment a great number of times, you would obtain a significant result 99% of the time. Okay. So again, we ran an experiment. It's two sample groups here. We have a p of 0.01. Right. And the question is, which of these, getting that p of 0.01, which of these 6 are true? And it, again, could be all or none. So so whenever you're ready, type into chat, right, which ones of these you think we can correctly conclude from p of 0.01. All right. I see a decent number of brave people putting in answers. So let's go through these one by one. So I think most people agree the first few are not correct, right? So you have absolutely disproved the null hypothesis. Almost any statement with absolutely in it is never going to be right in statistics, right? So we can pretty much rule out like 1 and 3 right off the bat, right? Okay, 2 is you found the probability of the null hypothesis being true. And so that is a common interpretation of a p-value, but it's not what a p-value is, right? Because the p-value is assuming the null hypothesis is true. What's the likelihood of this data, right? To compute the probability of the null hypothesis being true, we would need to use Bayes' rule, right? We need to actually, for example, weight by our prior belief in the null hypothesis, right? 4 is you can deduce the probability of the hypothesis being true, which is not the case. We would need to know extra information like the prior in order to figure that out. Okay, so let's get 5 and 6, I think, are definitely the trickiest. So 5 is, if you decide to reject the null hypothesis, the probability you're making the wrong decision. this one I myself got fooled by this because I thought this sounds kind of right, but this is actually the same as 2. Right? If you decide to reject the null hypothesis, the probability you're making the wrong decision is the probability that the null hypothesis is true. Right. So 5 is actually the same as 2, just written differently in a confusing way. So, right, if you decide to reject the null hypothesis, the probability you're making the wrong decision is the probability that the null hypothesis is actually true, which again, we don't know in this data, right? We would need to like use Bayes' rule or something to figure that out. And 6 is if the experiment were repeated a great number of times, you would obtain a significant result on 99% of occasions. So this 99% would be a measure of power, which we can't really which we actually can't really compute here. Again, this would require some extra assumptions to figure out what this is. A p-value of 0.01 doesn't mean that we're going to get a significant p-value 99% of the time. Right, we basically have to make some assumptions about what the actual curve of effect sizes and stuff are here, which we don't know from a single experiment. So the correct answer here is actually none. And if you didn't type none, you shouldn't feel too bad because they ran this experiment in 2002 and found that when they surveyed statistics and structures, 80% of statistics and structures made at least one mistake, right? They marked at least one true. When they surveyed psychologists that were in the field not teaching methods, about 90% of them made at least one mistake. And when they surveyed a psychology class, every single student got it wrong. So, there's some earlier studies too. This is from like a 1986 study that again found like similar rates of this. So, right, the conclusion here is that p-values are really hard to interpret. It's really hard to like properly say what a p-value is, especially if you're like teaching stats, you have some hope, but like otherwise it's basically hopeless that people are gonna know what a p-value is. And this is again people that are these are like actual scientists in the field. This is not even talking about like the lay public trying to understand this. And I mean, so at least some of this confusion actually is coming from textbooks as well. So here's another study looking in statistics textbooks and found that in the majority of them, there were at least one of these fallacies. So there was a sentence in one of these textbooks that was equivalent to one of these false sentences, right? And so this is saying that like not only are the students confused, but the textbook writers are confused, which of course is continuing to confuse everyone. So this is one of the arguments people make against p-values. And so there's been a lot of thought about what we should do about this. There was an interesting special issue of the American Statistician Journal last year looking at like what we should do, right? What can we do that moves beyond sort of classical significance null hypothesis tests? And so there's lots of interesting papers. These are all basically like opinion papers from statisticians about, right, like what have we learned or not learned from p-values? Why is getting rid of p-values so hard? And so, right, some of these questions are just about sort of like norms in the field and questions, right? There's some articles here that are arguing sort of in favors of p-values, that people criticize p-values because they don't really understand them, but if they did understand them, they would like them. Articles that maybe if you as long as you interpret p-values correctly, they're fine. And then the sort of most like extreme view on this is that we should like stop doing null hypothesis tests. There's some big names here, especially Andrew Gelman is a big name at Columbia Stats, right? That we really should just like stop doing null hypothesis tests. They're too confusing, and the Bayesian approaches give us something closer to what we actually want from experiments. So again, part of the conclusion here is simply that people have many varying opinions about this. In practice, you're usually going to do the stuff that's familiar in your field. But I would, if you are doing research and publishing statistical tests, I would encourage you to think about expanding your horizons to some of these Bayesian methods. There's no reason you can't report both regular p-values and some kind of Bayesian result in your paper, right? You can certainly do both, which is sort of a good outcome that way other people doing frequentist tests can understand, but you can maybe also get some more sort of interpretable things out. I think this is especially critical, and I'm going to, in the lecture next Thursday, I'll talk about this a little bit too, that in situations where the public or policymakers is going to be making decisions based on your work, it is really important that no matter what kind of approach you use, that you explain the result, right? And you contextualize the result in a way that people can understand. Just spitting out a p-value is almost certainly going to confuse people about what it is that you found, right? And so, right, writing out sort of a clear description of what the statistical evidence means, and right, what this evidence is, what the strength of this evidence is. Things like confidence intervals, for example, I think tend to be more interpretable than p-values, right? That can tell people, here's our range of guesses that are consistent with this data. And so in general, I think p-values are a pretty bad way to communicate science to the public. Maybe they're even a bad way to communicate it among scientists. But right, this is a sort of broader question about how we actually get actionable evidence out of our data. Okay, so to sum up, again, the conclusions of these Bayesian stats, I think in many ways are more intuitive. We can also find evidence in favor of the null, and we can compare any set of hypotheses. Another downside to these Bayesian methods is that they do tend to be kind of math heavy, not just in terms of understanding them, but even there's more like fundamental problems that these are hard things to estimate mathematically. So many times there's approximations we can use. Again, a lot of these tools are way easier to use than they used to be. So if you'd like to run a Bayesian version of a t-test, for example, there's easy R packages to use that basically it works pretty much exactly the same way as the t-test you've been using in R, except that under the hood it's doing Bayesian stuff. You do also have to specify a prior over your prior belief in things like what the effect size is. But it has a lot of these packages have sort of like suggested things. So if you run a Bayesian correlation analysis, for example, it'll have sort of a default prior in there, which is that your R value is centered around 0 up to plus or minus 0.5 or something like that. So there is a little bit of extra assumptions you have to put in, but at least for simple versions of these Bayesian tests, they're not any harder to use, that someone else has already done the hard work of writing these functions for you. And so, the reason that we just shove in this topic in this single week of the course is because this is still not that popular in psychology, but it is becoming more popular. Maybe a few years from now, this class will be more like half and half classical stuff and Bayesian stuff. And they can be these Bayesian methods can be hard to understand, but there's some debate about whether p-values are really easier to interpret. They do require things like setting a prior. They do require things like thinking about what questions we want to ask, right? One sort of advantage of Bayesian methods is that we can ask more questions, but it means we also have to think more carefully about the questions we want to ask and what models we want to build. All right, any last questions? All right, so there'll be one more week of classes next week. On Tuesday, we're going to do kind of a high-level overview of stuff we've talked about in the class and talk about when you should use different methods. And then Thursday will be the optional lecture looking at some of the stats fights that are going on, like literally right now on Twitter about things that are currently happening in the world. I think it'll be an interesting class. It won't be required for the final project at all, but yeah, I think we'll have some interesting things to talk about. All right, great. See everyone next week.